Let's learn integration by parts. We're going to start with y equals uv. First, let's figure out how this works. That's a product. Remember the product rule. We're going to take a derivative of this or find the differential. Product rule is derivative of the first times the second plus the first times the derivative of the second. So when we apply that to here, we're going to say dy equals the differential of the first, du times v, plus the first times the differential of the second. Now let's take this and we're going to rearrange this. I want to solve for u dv, and I'll just put that over here to make it a little bit easier to see. And so we'll move the du v to the other side, except we're going to put the du at the end. So we'll have dy minus v du. Now what we want to do is integrate that. So we will take the integral of all of it, and then we'll have the integral of u dv equals the antiderivative of dy would just be y minus, and we don't know this one, the integral of v du. And then what is y? That's just uv. And so we get this, and this is the method of integration by parts. All right, so let's see, when we have here, another way to look at this that you may see is it'll be f of x times g of x. So in other words, and then dx. What this is when we have two functions multiplied together. That's kind of how we recognize that we might use integration by parts. This first one is going to be, or one of them basically, is u, and then the part with the dx will be our dv. And then when we're applying that, we're going to end up saying u times v. It's a good thing to write it until we get that down, minus the integral of v du. So one thing about dv is, in fact, write this down, it must be something that we can integrate. If we keep that in mind, it should flow fairly easy. So it must be something to integrate that. So let's take a look at type 1. Integrands of the form x to the n, e to the ax, x to the n, sine of ax or cosine of ax. So when we're looking at this one, we have two functions here. We have x and sine of 6x. Which one is the one we want to let u and dv be? Well, we can integrate both of them, but when we're doing this, if there's a choice, we want to make our new integral simpler. So what we're going to do here is let u equal x. And if u equals x, that means dv has to be the rest of the stuff. So that would be the sine of 6x dx. And this is an important thing too. Everything in the integrand must be taken into account. Everything in the integrand. So we need to now find du. That's just going to be dx. And then find the antiderivative. And so the antiderivative sign would be negative cosine of 6x. And we got to take care of that 6 that would come out from the chain rule. So we get negative cosine 6x over 6. And now let's apply it. So we have I equals u, which is x, times v, negative cosine 6x over 6, minus the integral of v, negative cosine 6x over 6, du, which is just dx. So then over here we have, well, let's put this in parentheses first, right, because we have that negative there. And we can simplify that part. Once we do, we have a fairly simple integral here to find the antiderivative of. Over here we can just write negative x over 6 cosine of 6x. Then we can say what is, let's see, this would be 1/6, and then the antiderivative of cosine of 6x would be sine of 6x over 6, and always remember our c. And at this point we just need to clean it up just a little bit, so we can say negative x over 6 cosine of 6x plus, you can either say 1 over 36 or sine 6x over 36 plus our constant c, and that is it. Let's apply this one. This one's going to be slightly different just because we have an x squared here, but it's going to start off similarly. We'll say u equals x squared, and then dv will be cosine of x dx. So then du is 2x dx, and v is sine of x. And apply it, and we get uv, so x squared sine x minus the integral of v sine x dx, so it would be 2x dx. And we look at that and say, well, I don't know how to integrate that, but it is better because now we only have a degree 1 for the x instead of a degree 2, so it made it better. And what do we have to use? Well, it's still of the same form, so we're going to have to use integration by parts once again. So what we can do here is take out that 2, and I'll show you kind of leaving it in and taking it out. And we'll have x sine x dx, and we'll just carry this other part down. But when we do this one, we can't use u again. We're going to use u sub 1 will be x, because we've already used u. So u sub 1, du sub 1 is going to be dx, and then dv sub 1 will be sine x dx. So v sub 1 will be negative cosine of x. And I'm just going to put it over here. So we are going to carry over our first part. At this point, that is done. Nothing will change that. But we'll have negative 2, and we'll put it in a bracket. And now we go the uv idea again. So we'll have x and negative cosine of x. So we'll go negative x cosine of x minus the integral of v negative cosine of x. And again, let's put that in parentheses. And then dx. Now we've gotten it down to, this is a simple integral to find. Overall, it's not bad. Let's multiply this negative 2 as we go through, so that'll end up being plus 2x cosine of x, and we have a minus and a minus. We'll make it a positive, but we'll have negative 2. The antiderivative of cosine x will be sine x, but we have a negative 2 there, so we'll have negative 2 sine x, and then plus c always. And that's it for there. Now, how can you tell by looking how many times you're going to have to use integration by parts? Hopefully these two examples show. The first one was degree 1 for that x, the polynomial, and the second one's degree 2. First one we did once, second one twice, so it's going to be the degree of our polynomial. Go ahead and write that down. All right, type 2, integrals involving ln of x or any log function or inverse trig function. So what we did last time was we let u equal the x squared or x or whatever that polynomial was. But remember, the idea behind it was, what can we integrate? On the previous one we could do either one, but letting u equal the polynomial made it simpler. In this case, we can integrate only x squared. We don't know how to integrate ln of x, so what we're going to do is let u equal ln of x. So du is 1 over x dx. dv has to be the rest of the stuff, so we have x squared dx. So v, the antiderivative, would be x cubed over 3. Now some might be thinking, hey, that looks worse. We have x cubed. Let's see what happens. We have I equals the integral of uv. So we have x cubed over 3 ln of x minus the integral of v x cubed over 3 dx 1 over x dx. And look what nice stuff happens there, because we can simplify this. Let's pull out that 1/3, and we get the integral of x squared dx. And we'll just copy down the other stuff. So we have the antiderivative of x squared, x cubed over 3, always tack on our plus c, And now it's just a matter of cleaning things up just a little bit, and we'll say x cubed over 3 ln of x minus x cubed over 9 plus c. And that is it for that example. Let's take a look at this. Here's a rule, lipit, that can be used. It's not something I typically use, but I'll show you. And L stands for log. It's a way to let u, what you want to let u equal. So if you do it in this order, it will work. I stands for inverse trig. P stands for polynomial. E stands for exponential. And then the last one, T, stands for trig. Now if you do this, it will always work. It doesn't have to always be in this order for trig, exponential. They can be reversed, but when you do it integration by parts multiple times in the same problem, you have to just be consistent and always let u equal either the exponential or the trig one. Let's take a look at number 4. On this one, some people initially have a hard time looking at it and say, okay, what am I going to let u and dv be? U is going to be our inverse trig one, so we have inverse sine of negative 3x, and dv is everything that's left. In this case, it's just dx. Now you can, if you forgot how to find your derivative of your inverse trig functions, and specifically inverse sine, go ahead and rederive it. You can say sine of u equals negative 3x, set up your right triangle, find the derivative, and then plug it all in, or you can remember the rule and apply it. I'm just going to do that right now. It's 1 minus the argument squared, so negative 3x squared, times the derivative of the inside, and in this case it'll just be negative 3, and we'll have dx. And so v, the antiderivative of dx, will just be x. Let's plug it all in. So we have uv x inverse sine of negative 3x minus the integral of v du. I'm just going to multiply that stuff out. So we'll have negative 3x over square root of 1 minus 9x squared dx. Now, when I do this, let's first make that a positive. And now we have just another integral, and we have to use any of our techniques to do so. When I look here and I see this is a degree 2 expression, and I have degree 1, I should be thinking derivative here. So let's go ahead and see if we can make a substitution. We have w equals, I don't want to use u, I've already used that one, 1 minus 9x squared, so dw is negative 18x dx. Move that 18 over to the other side, and we have x dx. I have that here, and now I can go ahead and do my substitution. So I have 3, the integral negative 1 over 18 dw over square root of w. And we're just going to bring this other stuff down, x inverse sine of negative 3x. I just need to simplify a little bit. We have negative 1/6 integral w to the negative 1/2 dw. So I'll have negative 1/6 w to the 1/2 over 1/2, or multiplied by 2 over 1. And then we'll tack on our plus c. Let's go ahead and write our inverse trig here. And simplify. This will be negative 1/3. Go ahead and substitute back in for w. This would be square root of 1 minus 9x squared. Have our plus c. Write that first part because that's not changing. And that is it for that type. All right, now type 3, we're looking at integrals of the form e to the ax sine bx or cosine bx. So when we're doing that, what we want to do is say, what are we going to let u equal and dv? Well, if we follow the lipit, we'd say it's the exponential for the u. Now, like I said before, it really doesn't matter. You can have them switch, but whatever you do, you have to be consistent when you use integration by parts multiple times. So let's go ahead and do that. I'll just go ahead and use the u is the exponential part, so then du equals 2e to the 2x, and then dv will be everything else sine x dx, and the antiderivative sign would be negative cosine of x. So let's go ahead and plug it in, and we'll have I equals uv, bring the negative in front, e to the 2x cosine of x minus the integral of v negative cosine x, let's throw that in parentheses because of the negative, and then we'll have 2e to the 2x dx. So we look at that and we compare it and say, can we integrate this? No. In fact, it looks a lot like the other one. You wouldn't necessarily know right away by doing this, but let's go ahead and try integration by parts one more time. So we'll let, in this case, actually let me go here, we'll go u1. Again, we have to be consistent. And the previous one I factored out at 2. This one I'll leave it in just to show that it really doesn't matter. So we'll have 4e to the 2x dx, and then dv1 will equal cosine of x dx. And we get v1 equals sine of x. So let's go ahead and plug that stuff in, and we'll have uv, so it'll be 2e to the 2x sine x minus the integral of v sine x times du, so e to the 2x dx. And this other part we're just going to carry down. So what do you notice about this? Maybe I could rewrite it here. I'll put the 4 out, and I'll say the integral of e to the 2x sine x dx. Compare that to the original. In fact, it is the original, so what this really is 4i. Let's go ahead and just copy this part. It's pretty done, pretty much. And we have equals I. Now we can just say, hey, let's add it to the other side. We get 5i equals all that stuff divide by the 5, and we get negative 1/5 e to the 2x cosine of x plus 2/5 e to the 2x sine x, and at this point we'll tack on our plus c. If we did it earlier, we just have to divide by 5, and a constant divided by 5 is still a constant, so instead of putting it earlier, we just tack it on at the end. So in this case, you're going to have to do integration by parts, and you're going to get the original integral back, and then when you move it over, you'll have that constant, and the coefficients of the terms will change. All right, let's take a look at the next one. The next one's a cool problem. It's an interesting one. It's going to combine different ideas, different methods that we have used. And let's see what happens with it. So if we start off the way we normally do and say, let u equal root x, du is 1 over 2 root x dx. And normally we'd say, hey, that looks bad because we don't have that 1 over root x on the outside of it. If it was just a constant, no problem. We could take care of the constant, but we can't do that with a variable. We can't have that variable inside. We can't introduce a new variable. In fact, what I want to do here is, because I know what's going to come, I'm going to change this to a w. So what would happen here could I figure out what dx is? Well, I have dx here, but it has this 1 over root x and then 1 over 2 root x. We could easily move that 2 to the other side, right? So then we just have 1 over root x. Let's compare these. If I multiply these two together, I can have w dw and then root x times 1 over root x, and I'll get dx. And that's exactly what I want. Now, you might say, yeah, but how am I going to see that? Yeah, I agree. There's another way that I like better. And we have w equals root x, so how about let's solve for x, and then we can find dx easily. So x equals w squared. Now when we find the differential, we have 2w dw equals dx, and that's nice and simple. So now let's go ahead and plug this stuff in. We have dx, and we have the u, or the substitution e to square root, so it's going to be e to the w times 2w dw. And now you can see why I put this in with integration by parts. If we take out that 2, we have w e to the w dw, and now we can do our integration by parts. U equals w, du equals dw, and dv equals e to the w dw. V is e to the w. We can say 2 times uv w e to the w minus the integral of v e to the w dw. And on this one, I'm going to do a couple at the same time. I'll multiply it out. 2 w e to the w minus the antiderivative e to the w is just w, and we have that 2 there, so 2 to the w plus c. Now, our original one was in terms of x, so we need to move it all back to x. So we have square root of x and e to the square root of x minus 2e to the square root of x plus c, and look how cool that problem was. Now there's one more idea that's really neat. Let's take a look at it. All right, our last one, integration by parts, but this time it's going to be tabular integration. And you might say, we've already did this. Yes, this is type 1. We have x cubed e to the 2x. But how many times do we have to do this? 3 times because of the degree of the polynomial. But that sounds like a pain. And there's another way to make it go faster. So let's come over here, and what we're going to do is just write u, and we're going to find the derivative and dv, and on that one what we're going to do is integrate. So let's kind of put it here. So our u will be x cubed, and our dv will be e to the 2x. When we're doing it in this method, we're not going to write the dx with it. So all we do is we find the derivative of each of the u1s and just go down in our table until we get to 0. And then we find the antiderivative of the e to the 2x part. So we have 1/2 e to the 2x, and then 1/4 e to the 2x, 1/8 e to the 2x, and the last one will be 1/16 e to the 2x. So when we're applying the integration by parts, it's going to be uv, that's a positive, minus the integral of v du. Well, it turns out this one is going to be v du, and it's going to be minus that. And then you have to use integration by parts, and the next time it's going to be minus, but it's a minus of the minus, so that will end up making it a positive. And on the third time, you have to do a minus, and a minus, and that will give us a minus. And so it just alternates positive, negative each time. And at this point, we just need to write it all down. So we multiply these together. We'll take the 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus 6 times 1/8 will give us a negative 3/4 x e to the 2x. The last one, 6 times 1/6, and it's going to be minus, will give us a 3/8 e to the 2x. And when we go the next one, 0 times any number is 0, so we tack on our plus c, and we're done, and that is it.